In this video, we're still solving exponential equations, but we've got some other properties of exponents that we need to use in order to solve these equations. If you look at these two examples here, what we see is in each of them we have some fractions. What we're going to utilize here is that property of having a negative exponent. So if I want, I could rewrite 1 over 6 as 6 to the negative 1 power. And I would no longer have the fraction. But that's still equal to 216. So I still need to get the same base, just like I have in my other problems I've completed, in order to solve for x. Well, the other day we said that 6 squared is 36, and when we multiply that by 6, we get 6 cubed is 216. So we can write this equation as 6 to the negative 1 times x is this equal to 6 to the third power. And we also know that when we have a power to a power, we can multiply those exponents. So this is actually 6 to the negative 1x equals 6 to the 3. Now that we have the same base, I can set negative 1x equal to 3, divide both sides by negative 1, and we find that x equals negative 3. So if I were to substitute negative 3 in for x, I'd have 1/6 to the negative third power and to write this with a positive exponent, that would be the same as 6 to the positive 3. And that does, in fact, equal 216. So this does work. I can do something similar with example B. I have 5 to the x plus 3 equals 1 over 25. I can't exactly change my base of 5, but hopefully you recognize that 25 is the same thing as 5 squared. So we could write this as 5 to the x plus 3 equals 1 over 5 squared. But we still don't have the same base because we still have this fraction. So we can rewrite that fraction, and actually we won't have a fraction. We can rewrite that expression with a negative exponent as 5 to the negative 2 power. Now that we have the same base, we can set the exponents equal to each other. X plus 3 equals negative 2. Subtract 3 from each side, and we have x equals negative 5. So again, if I check, 5 to the negative 5 plus 3 would be the same as saying 5 to the negative 2, which is equal to 1 over 5 squared, which has the same value as 1 over 25. We have done this problem correctly. So we're utilizing the property of having a negative exponent or rewriting things with negative exponents. Here, in this first example, I have 12 times an exponential expression. Now, if I want to solve for an exponent, I need to actually have that exponential expression isolated. So I need to ask myself, how do I undo 12 times 2 to the x minus 7? Well, in order to undo a times, in order to undo a multiplication, I would need to divide by 12. So I'm going to divide both sides by 12. And that will leave me 2 to the x minus 7 equals 2. The nice thing here is I do have the same base, but I notice I don't see an exponent on the 2 that's on the right side of my equation. So I remind myself, oh, that just means that the exponent is a 1, because anything to the first power is equal to itself. And then we can write x minus 7 is equal to 1. Add the 7, and x will equal 8. And again, we can check. "12 times 2 to the 8 minus 7 would be the same as 12 times 2 to the first power, or just 12 times 2, which is in fact 24. Now there's a couple of things we need to do with this one on the right. I see they both have a 12, but on the right side here, we have a radical expression. So we need to write that radical expression so that it has a rational exponent. So we have 12 to the 2x minus 1 will equal 12. Remember, the index of your radical is your root. So this becomes 1 over 4. So 12 to the 1/4 power to the x. And because I have a power to a power, I can write this as 12 to the 2x minus 1 equals 12 to the, when I multiply these, 1 times x is x over 4. I have the same base, so now I can set the exponents equal to each other. 2x minus 1 equals x minus 4. Now, I know I have a lot of students that don't like fractions. They see a fraction in an equation and they're like, what? Well, if I want to undo this fraction, remember fraction is just dividing. Multiply everything in the equation by the denominator of your fraction. Take 4 times everything in this equation. So 4 times 2x is 8x. 4 times negative 1 is minus 4. And when I take 4 times x, that's 4x divided by 4, and we have x. Subtract 8x to isolate x to one side. And we have negative 4 equals negative 7x. Divide both sides by negative 7. And we have 4/7 equals x. Not exactly the nicest of numbers, but we could still check this. So if I check, let's see, we'd have 12 to the 2 times 4/7 minus 1. And remember, this became 12 to the x over 4, or we could write it as 1/4 x. That might be easier. So let's write it as 12 to the 1/4 times 4/7. And see how these two sides simplify. So 12, this would become 8/7 minus 1, but in order to subtract, I would need a common denominator, so that's a 7, so 1 is equivalent to 7 over 7. And when I multiply over here, I would end up with 12 multiply straight across, that's 4 over 28. I can still simplify on each side. 8 sevenths minus 7 sevenths is 1 seventh. And 4 over 28 also simplifies to 1 seventh. So even though this exponent of 4 sevenths, or this value of x of 4 sevenths, didn't look nice and neat like a whole number, it still worked out to be the correct answer.